All right, in this video, we'll be looking at complex circuit practice 3. Again, to investigate these circuits, we're using our key ideas of Ohm's law. That tells us the change in potential across a resistor is based on its resistance and the current going through it. Our other ideas are the idea of conservation of charge, which says that if I have a current coming from this battery and it reaches a junction, a split, some of the charge is going to go one way and some is going to go the other way. But the total, if I call this I1 and I2, the total current is going to be conserved. So if I have 5 coulombs per second going in here, overall, these two together will be 5 coulombs per second, 5 amps. And that's not what it actually is for this problem, but just as an example. And as they come back together, charge is still conserved, so I get the same total current I started with when these two join back up. So that's our second rule. So we've got Ohm's law, and we have this idea of conservation of charge, telling us how the charge is behaving, how it splits and reforms in the circuit. The last rule is the idea of conservation of energy, where if I have an electron and we say right before the battery it has no energy, the battery is going to give it electric potential, certain amount of joules for every coulomb of charge. In this case, 30. We pretend the wires themselves have no resistance, which means they don't take away any energy. So if right after the battery it has 30 joules per coulomb, 30 volts, it keeps all that energy as it goes around the circuit. Now when it gets to a junction, the electron can be flowing with this current or with that current. Let's say it goes this way. This resistor now takes away some energy because it has resistance. And Ohm's law would tell us how much delta V equals IR. So this electron, it gained 30. It didn't lose any here because there's no resistance. Here it lost some energy. Keeps going, no resistance here, and it's perfect wires. Now again, it loses energy. And then keeps that same energy because there's no resistance in the wire. And we know, due to conservation of energy, that going around, it's going to be 0 back at the end here, because we'll find if we looked at power, battery's giving a certain amount of power, these are taking away a certain amount. If it didn't get back to 0, that means we're somehow creating extra energy, or we're somehow losing energy to something that's not one of these resistors, which shouldn't happen. So that's why as I go around, I get back to 0. Now, that was going around this way. Same thing has to happen going around here. And we'll notice, because there's no resistance anywhere in this part, that means that this all has to be at the same energy level. So these each have to both drop it the same amount. So this is what we would call being in parallel for that to happen. Because as an electron goes across here, loses something, loses something, loses something, loses something. Both paths involve losing this amount. Therefore, these also have to change the same amount so that both paths work out to giving me 0 change in energy overall. All right, so those 2 and 3 ideas are the key major ideas of this unit, and everything that we do is with those 3 ideas. All right. So to help us out, we like to draw a table to organize information about the circuit. So let's see, I'm going to call this resistor 1, and the reason I'm calling resistor 1 is because I called this I1. So I'm going to say resistor 1 has a current I1 going through it. I'm going to call this resistor 2 because I said this was I2, so it matches up, which means this will be resistor 3. Resistor 3 has the current, the total current, just which we're calling I, going through it. So I'm going to pause and construct this table. All right, so in my table here, I've added the 3 resistors I knew. I've added, I know, the voltage of the battery. It's adding 30 volts to the charge that moves through it. And that's everything I'm given initially. So my goal now is to find more information to help me figure out everything I need to know. I need to know these currents. I need to know these voltages. Okay. So right now, looking at my table, there's not a lot here. It can't really help me. I can't really use Ohm's law without knowing 2 things about each of these resistors. So I could do a bunch of complex math knowing that I equals I1 plus I2. The voltage changes 0 across all these. Or I could take the shortcut. And the shortcut is saying we know how to take a bunch of resistors and pretend that they're just one resistor, an equivalent resistance. So in previous videos, I've talked about why we can do that. But here, when I look at it, I'm looking for resistors that are either in series with one another, so they have the same current, or I'm looking for resistors that are in parallel. They have the same change in voltage. And I see that 1 and 2 here are in parallel. So I know there's a rule that lets me combine resistors 1 and 2. And that's 1 over R1 plus 1 over R2 can give me a combined equivalent resistor, which I could call R12. This equation is because they're in parallel. This is how the math works out for that. So we have 1 over 20 plus 1 over 40 equals 1 over R12. So that's 40 over 3 equals R12. Because when I add this, this is 2/40 plus 1/40 is 3/40, and then I have to reverse everything to get 40/3 ohms, which is a 13.3 repeating ohms. Great. So let's redraw this circuit. With our new combined resistor. So this circuit, our original circuit, will behave exactly like this equivalent circuit in terms of the current coming from the battery and all that. Okay. So that's pretty cool. That can maybe help me. What am I exactly trying to find here? I'm actually trying to find this current, because if I can get these down to just one resistor, I can find the battery's current. So that's usually the goal with this equivalent resistance process. That's when we'll usually use it, is to help us find the battery's current. So I still have 2 resistors here, so I'm going to take one more step. If I look now at the current, there's one current here, unbroken, unsplit, no junctions, which means these are in series, and I can add them together. So 30-volt battery, 23.3 ohms. Now if I looked at this, now I know the change in voltage from here to here, because I have 0. If I say before the battery is 0, I say after the battery is 30. Unlike here, where I didn't know this purple, so I didn't know any changes. Here I do, because I've made them one resistor. I can see and look and say, okay, it's changing it by 30. So delta V IR 30 volts, I 23.3 repeating ohms. Do some math on that. 30 divided by 23.3. Throw a bunch of extra threes in there because it's repeating. We're going to round this to 1.29 amps. So that's the current produced by the battery in this simple circuit. And we know that this circuit is equivalent to this. So my I coming from the battery is going to be 1.29 amps. So 1.29 amps. Now let's see what that current's doing. I got 1.29 amps. It's flowing. It's splitting up. It's coming back together as 1.29 amps. So this 10 ohm resistor is getting 1.29 amps. I encourage you as you're watching this video to maybe try and pause at certain points and see if you can figure out what the next step would be before I do it. So here now that I know the current through this resistor, and I know its resistance, I can find how much it's changing the voltage by. Oops, sorry, I put this in the wrong spot. 1.29 amps is going through resistor 3. So resistor 3 has a voltage change of 12.9 amps. Delta V equals IR, so RI equals delta V. And that should be volts. Okay, so I just learned something about this resistor. I've learned it's changing the voltage by 12.9 volts. So if beforehand, I always like to say before the battery is 0 volts. So after the battery is 30 volts. Beforehand, I have something. I'm losing 12.9 as I go through this resistor. And afterwards I have 0. Well, if I start with something, lost 12.9 and have 0, that means I started with 12.9 volts. Great. So now I know the potential at location B. Last thing I want to know is some currents. There's two ways I could actually do this. One's the normal way, and one is a little bit of maybe a quicker way. Looking at these resistors, I can see this one on the left has half the resistance of the one on the right, but they have the same change in voltage, which means I know to get the same change in voltage, this one's going to need twice as much current because delta V equals IR. So if I have half the resistance, I'm going to need twice as much current to get the same delta V. So I know this one needs twice as much current, and I know that together they have a current of 1.29. As we wrote here, we said that I1 plus I2 has to be the total I. But looking at this and seeing this as half the resistance, I know I1 has to be twice as much as I2. So I could write, I1 is twice I2. 2I2 plus I2 equals I. So that's 3I2. So the current through this path here, I2, I know is going to be a third of the original current. And that would mean that the other one has to be 2/3 of the original current. So together, I get the full current. And I was able to say this because I noticed that this has half the resistance. So it gets twice the current that this one does. So I could do 1/3 times 1.29 and 2/3 times 1.29 to figure out the current. Now let's say I didn't make that observation. That's okay, because I know the change in voltage here. I know it's going from 30 out of the battery, and it's losing a certain amount to get to 12.9. Well, how much is it losing? The difference between 30 and 12.9 is 17.1. So I can say resistor 1 is changing the voltage by 17.1 volts, and the same thing for resistor 2. Whether the electron goes this way or if it goes that way, it needs to lose 17.1 volts down either path. And from there, well, now I know the delta V, I know the resistance, I can find the current necessary to make that happen. So 17.1 divided by 20 is 0.855 amps. 17.1 divided by 40 is half of that, 0.4275 amps. And if we had done it this way, we can see that our original current, 1.29 divided by 3, is 4.43, which is this rounded up. And this would be twice as much as that, because you'll see this is twice that number. So that just confirms this method as well. Especially good to check our work. These two together, if we added them up, we should get back to 1.29, which we do. 0.855 plus this with some rounding, because remember this was rounded as well, gets us back to our original current. So conservation of current is satisfied. Oh, we forgot we could have added here the battery also has 1.29 amps through it if we wanted to make sure our table was completed. Great. All that remains, I guess, now we finished the table, so we know everything there is to know about this circuit. So now we can answer the actual question, determine the electric potential at and the current through each location. Location A, B, and C, the potential and the current. Oops. A, 0 volts. I'm just reading my picture now. C is in the blue, 30 volts. B is in the purple, 12.9. Current-wise, A has the full current going through that spot, 1.29 amps. B has the current that's going through the outer loop here, which we found I2 to be 0.43 amps. Just rounding that. And then C is on the center loop here, which is the current going through this guy, 0.86 amps. Great. Now let's look at this next guy. In this situation, I am not given one of the resistors, but we will still make a table. All right, here's my table. I added the resistors. I don't know R yet. That's what I want to know. I got the battery. And I was told this current coming out of the battery is 2.67 amps. So I followed that current. I saw it was going through the 6 ohm resistor, splits up, comes back together. So it's also going through this unknown resistor, which I labeled as resistor 4. So I added those to the table. Some other things I'm going to do just to do it is draw, okay, this current's going like that. It's splitting up here into the current through the second resistor and the current through the third resistor. And then it's coming back together to go back through the battery. So we can see 6 ohm is getting the full thing. These are not getting the full thing, so I cannot fill that out just yet. I can say that, again, I have a current going in as I, current coming out, these two guys. And current has to be conserved. So these two together need to add up to the current going in. So knowing this information, it looks like I can find the delta V for this resistor here, the 6 ohm resistor, because I know its resistance, I know its current. 6 times, I assume that's actually 2.6 repeating. Yeah, so 16, colors. 16 volts. All right, so how does that help me? Well, we just found voltage, so let's do some coloring of that before the battery, after the battery. Changes here to something, changes again, something else. We just found out this change. We just found out this change was 16 volts, according to our table here. So if before I had 80 volts, and I changed by 16, I'm down to 64 afterwards. 64 volts. Great. Now, what can I do next? I still have some issues. I don't know this area here, the potential. So that makes it difficult to find the change across these resistors. Can't do anything with this guy. I don't know his resistance. I do know his current, but I don't know his delta V either. So I might be stumped here. This is actually a very challenging step. Easy to get stuck on. But we do recognize, I'm not saying we do recognize, it's hard to see this, that this resistor is half the resistance of this one, which means this one's going to get twice as much current, because if they're going to change the voltage by the same amount, and delta V equals IR, that means if this has half the resistance, it needs twice as much current to get the same delta V. So we can use that. We can use that idea to help us find what that current is. So we know the current through 3 has to be twice the current going through 2 here, because it has half the resistance but same delta V. And we know current is conserved, so I has to be I2 plus 2I2. So I2 has to be a third of the current. So this is twice as much current. They're sharing the current. So this gets 2/3 of it. This gets 1/3 of it. So the current was 2.67. This one gets a third of 2.67. It's 0.8888. Another one gets 2/3 of 2.67. 1.77 repeating. Amps. All right. And now that I know those currents, so that was tricky. That was tricky because we had to really, really rely on this understanding of current being conserved, this splits, but they add up, and this idea of them both changing the voltage the same amount by being in parallel. And therefore we knew the ratio of the currents. Because we knew the ratio, this one was half of this. Now that we know that, we can find what that delta V is. We should get the same answer whether we do 60 times 0.8888 or 30 times 1.777, because we got those by saying they have the same delta V. Oops. So let's put that into our calculator here. Get 53.3 volts. Double check that by doing 30 times 1.7 repeating. 53.3 repeating, nice. All right. So that's their change in voltage. So if I had 64 changed by 53.3 repeating, I end up with, on the other side, 10.6 repeating volts. So now I can figure out R minus taking it from 10.6 down to 0. So that means if it has a current going through it of 2.67, changing it by 10.6, 10.6 divided by 2.67, that's an R of 3.97. With all this rounding, maybe that R actually ended up being 4, potentially. If we hadn't rounded anything, who knows? 3.97 ohms. Yeah, I just checked it. If you actually put in 10.6 repeating and 2.6 repeating, this comes out to exactly 4 ohms. So no rounding at all, that ends up being 4 ohms. All right, next. Similar to the first question, we're looking at these different spots and trying to find their potential. So I'm going to pause. I'm going to color this circuit, and I'm going to make a table. I'm going to make this resistor 1, 2, 3, 4, 5. All right, so here I have added all my resistors to my table. Battery is a 100 volt battery. And I've drawn, okay, the current, get the full current here. And it's splitting 3 ways, basically, down these paths. And we could label those, we could call this I2, I4, and I5. So this one's going through resistor 5, this one's going through resistor 4, this one's going through resistor 2. I could also call it I3, I guess. It's also going through resistor 3. Now looking at this situation, this is a situation where I have all the resistors and don't know anything about the currents. So this is a good opportunity to do some equivalent resistance. Trim this circuit down to one that we can find the battery's current for. Because once I do that, I'll know the current through this 8 ohm resistor. All right, so what can I trim here? I'm seeing these are in parallel, but they're not quite in parallel with these two because there's another jump going in here. But these are in series. I can shove those two together on the same line, same branch, so I can say this is an 18 and a 12. Together, that's 30. So let's draw that real quick. You could also just jump ahead to now combining the other ones if you wanted. So 3 resistors going on here. And the last one, 30, 45, and 10. And this one's my 8. These are now all in parallel. They are now all going. By combining resistor 2 and resistor 3, their combined resistor is going from that blue to purple potentials. So now I have 3 resistors in parallel. So 1 over 30 plus 1 over 45 plus 1 over 10. That does not look like an easy denominator. The denominator would be 90, I guess, because it's twice this, 3 times this. So that would be 3 times this, twice this, and to get this to 90, that's times 9. So that's 3 plus 2 plus 9 is 14 over 90. Then we need to flip it. So 90 over 14 is my equivalent resistor there. That's 45 over 7. That's not a pretty number. So we might as well get it in a decimal now while we're here. 6.43 ohms. So that was me combining the 3 parallel ones. So now I still have this 8, and this one's 6.43, so together .43 ohms. And now I can find the current, because by putting these together, now my potential change is the change from the battery, which was a 100-volt battery. So 100 volts over 14.343, 6.93 amps. And that's going to be my current here. That's the current through this resistor, and therefore is the same as the current through the battery. 6.93 amps. Well, back in my original circuit, I can see that 6.93 amps, as we said earlier, is going through the 8 ohm resistor. So 6.93 amps, resistance of 8 ohms. That's 55.44 volts. Delta V for that resistor. All right, so before, why did I lose my... Uh-oh, our sharing stopped. I'm not sure when exactly this stopped sharing my screen. Sorry about that. Looks like it's freezing up. It's not good. Just pause and try to figure this out. All right, I don't know exactly when that cut off, so let's recap what we did. We combined these two into one 30 ohm resistor. We then combined these 3 into 164.43 ohm resistor. Combined with the 8, that was a 14.43. That let us find the current in this simple circuit, which is the current going through the battery here. We said that current is going through the 8 ohm, and so the delta V is 55.44 over this 8 ohm resistor. Knowing that, if we have 0 on one side, that means this other side must be 55.44 volts. How does that help? Well, now I know the delta V for each of these. They're both going from the blue, which is right after the battery, so it's 100 volts. Battery gave 100. They need to be taking away enough to get me to 55.44. So 100 and 55.44, that's a difference of 44.56. So resistor 4 is doing that, and resistor 5 doing 44.56. And we lost our screen sharing. I don't know why that is happening. This is a 5. So knowing those values, we know the delta V, we know the resistance for each one. We can find the current required to make that happen. 44.56 divided by 45.99 amps. 44.56 divided by 10 is 4. We'll round up to 4.46 amps. Great. And that's these two branches. So conservation of current, I know the total I, which is coming in here is splitting into those 3, and current is conserved. So it has to be I2 plus I3 plus I4, or I5. Oops. We have I4 and I5. So we know the total current. We know that's 6.93. We know this is 0.99. You know this is 4.46. So we can find what this current needs to be. It needs to be 6.93 minus 0.99 minus 4.46. So it needs to be 1.48 going down this branch. So that's the current through the resistor number 2, the 18 ohm, and the current through the 12 ohm. 1.48 amps. 1.48 amps. Oh, the battery we found earlier, 6.93. All right, because we know this splits up into these 3 currents. Another way we could have solved this is we know that if we treat this as a 30 ohm resistor, it has a change in voltage of 44.5, which we found before. That's blue to purple here. So 44.56 divided by 30. Well, that's 1.48. So another way to do it there. And now I can find the delta V for each one. It should add up to 44.56. 18 times 1.48. 26.64. 12 times 1.48. 17.76 volts. And I can double check if I add those together. I get 44.4, which is close enough given that I was rounding things. Goes together. After it drops over both of them, it's dropped the same as these other two. Great. So now I can figure out whatever they wanted me to find out. Oh, I guess I can figure out what this green area is. The 18 ohm dropped by 26.64, so I was at 100. I lost 26.64, 73.36 here. 73.36 volts. Need to write really small here, so it'll be hard to do on paper. I'll try to make the circuit pictures bigger, I guess, in the future. Make sure if you're doing this on paper, you can write on these with enough space. All right, so we want to look at locations A, B, C, and D. And we want to know their potential, their electric potential, and their current. So A, 100 volts, and it has the full current going through it, 6.43 amps. B, we just found for B, 73.4, I'm going to round it, volts, and it has the I2 going through it, which we found was 1.48. C is here, potential of 55.4. And it's getting the current down the resistor for the 45 ohm branch, which we found was 0.99 amps. I wonder if we hadn't rounded if that would be exactly 1 amp. And D, it's in the blue, so same potential as A. We can see that because there's no resistors between A and D, so they should be at the same potential. Nothing's taken away any energy. And it has a current of 10 ohm here, 4.46 amps. Okay. All right, next up. Determine the potential difference across the battery. So we're looking for V for the battery. And we got this I that's going around like this. It's splitting up down these two paths and coming back together. Let's just call these 1, 2, 3, 4. We're going to pause to do some colors and make a table. All right, so this is the table. We've got the currents going through and splitting up. So the current, these two, 1 and 2, get the full current. The battery gets the full current of 2 amps. Don't know the currents here, but I know they're going to add up to 2 amps. Looking at this, 5 is a quarter of 20, so this is going to get 4/5 of the current if we wanted to do it that way. Don't know any delta V's, don't know the battery. Now, when I look at this, I could do some changes here. I could find these changes. And I also say, hey, I know all the resistors. Maybe there's something here I could do with equivalent resistance. I know the total current. Usually we don't know that. Usually we use equivalent resistance to find the total current when we know the battery. In this case, we know the current and want to know the battery. So this, if we can get this circuit to look like this, where we know what this is and we know what this current is, then Ohm's law makes it very simple for us to find the voltage. So even though I wrote this whole table out, and I could do it with the table method, in this case, equivalent resistance is going to be a real nice shortcut because finding the simple circuit tells me what I need to know here. So let's shove some resistors together. Might as well throw some colors on here to help us get that done. So these two are in parallel, same delta V. These two are in series, same current. So I'm going to sort of do both those at once. 1 over 5 plus 1 over 20. Multiply this by 4 and 4 for a common denominator. 4 plus 1 is 5/20. Flip it, that's 20 over 5, which is 4 ohms. Nice. And then these two, 82 plus 24 is 106. So my new thing here has looks like this. Where I have 106 and 4. All right, so these are now in series. Put them together. 110 ohms. All right, resistor 110 ohms, 2 amps. Delta V equals IR, which means delta V for this resistor is 220 volts. So this is 0, this is 220, which means the battery has a voltage of 220 volts. Cool. I don't think this is a long video already. We're not going to go through it the other way. Determine the potential difference if the current through the 30 ohm resistor is 2.25 amps. So we've got a current, it's going this way, it's splitting up. And this one is 2.25 amps. All right, splits up, comes back together, goes through this resistor and back through the battery. And we want to know another situation where we're looking for V. Now this one we don't know the full current, so we might have to do a table. Let's put some colors on here though. Okay, so looking at this, just some things I'm noticing. If I put these two together, they're in parallel with this one. I don't actually need to know anything about this spot here, so why not just start by putting those together? So they're in series. 50 plus 40 is 90 ohms. 30 ohms. And then this one is 2.5. I'm sure it'll make sense at some point. And then 2.25 amps through this guy. All right. And we'll cool. All right, so I have a current going here, splitting up. Call this my I. We label these resistors now that we've put some of them together. Let's just call them 1, 2, and 3. Then we can say the total I. If we look at this split right here, I is splitting into I1 and I2. But together, they make I. And then coming back, the full thing there. And we want to know this V. So we don't know exactly what's happening here, but let's make a table. So let's pause for that table. All right, pretty small table, only 3 resistors, and our battery. I was told the current going through this one. So hey, 30 times 2.25. That gives me a delta V. 30 times 2.25, 67.5 volts. So going from blue to purple is a change of 67.5. Resistor 1 is also going blue to purple. So it also has a change of 67.5. Well, now I can find a current 67.5 divided by 90. Because delta V equals IR. So current of 0.75. All right, so current going this way is 0.75 amps. Well, we just said the total current is these two together because it's splitting up. That means the total current has to be 0.75 plus 2.25, 3 amps. Great. And that's going to be the current through the battery and the current through resistor number 3. I like this question a lot. It's not as crazy as the other ones, but still requires us to use our rules of parallel and then conservation of current. Really great question. How does this help? Well, now 2.5 times 3, 7.5 volts. So now to find the battery, I know battery gives me a certain amount. I pick one of these paths to take, either one. I lose 67.5, then I lose 7.5, and I have to be back to 0. So it has to give me whatever 67.5 plus 7.5 is. I could also work backwards. I could say, okay, this is 0. This changed by 7.5, so this is 7.5. Then this changed by 67.5, so this is 67.5 plus 77.5 is 75. And therefore, going from 0 to 75, it's a 75 volt battery? And yeah, really great question. Not as much math and all this equivalent stuff we had to do, but still used a lot of our rules very well. Determine the value of R. So I have 5 resistors, each with resistance R. Then I have 2 guys here who look like they're in parallel. And then a 3 amps going through the battery. So sort of like the last problem. I see no reason not to shove these 2 together. So I'm going to. And then this might be easier to deal with if we also put all these together. So this is 110 volt 100 volt battery. It's got a current of 3 amps going through it. This I can all say is like one resistor with a resistance of 5R. And then these guys, I got 1 over 25 plus 1 over 20. And just some colors just so we can see that these are definitely in parallel since they have the same delta V. 1 over 25 and 1 over 20. Those share 100 as a common denominator. So that's 9 over 100. That's not a very nice number. 100 ninths. So going over here, we put them together. We have a resistance of 100 ninths, which is 11.1 repeating. Okay, and we had a current of 3 amps. And now we have a series circuit, so I can just say it's 3 amps everywhere. So I'm not going to make a table because we just have 2 resistors here. 3 amps, 11.1 ohms, that's a delta V of 33.3 repeating volts. So if I had 0 here, I have 33.3 repeating here. Got 100 here. So the delta V over this resistor is 76.6 repeating. 66. Oh, right, it's 2/3. Duh. So for this guy right here, delta V equals 66.6 repeating volts. And we know that equals IR, or in this case, I times 5R, I should say. So I is 3 amps. So 66 divided by 15, 3 times 5 is 4.4 repeating, basically, ohms. Similar case, except we're looking at in parallel. And the current through one of them is 1 amp. Well, if I look at this, they're in parallel. So they all have the same drop in voltage. So if this is 1 amp here, these all have the same resistance, that means this one also has to have 1 amp, and this one has to have 1 amp. And that's only because these three resistors are the same, which means to have the same change in voltage, they have to have the same current. All right, well, I have this current, and it's splitting into these three. So this current has to be 3 amps in order to split into 3 1 amp paths. Okay. 3 amps, 10 ohms. That's a delta V of 30. So if I had 0, I gain 30, up to 30. 40 volt battery, so this is 40. Now I can see for any of these resistors, they're taking it from 40 down to 30. That's a change of 10. Delta V is 10 volts. That equals IR. In this case, the I is the 1 amp because I'm not going to use 3 here. This is only as 1 amp. Any of these. 1 amp, resistance of R, dropping 10 volts. This is true for any of these paths. I is 1 amp. Oops. Oh, just rewrite. 1 amp. Doesn't look like a 1. So R has to be 10 ohms. 10 divided by 1. And there you have it.